as far as the prerequisites go, well, we did DLD 1. We'll probably use a lot of that stuff here in this class to put together these the sample CPU we're going to be doing, and understanding the other CPU we're going to be studying. We're actually going to be studying 2 of them. Electronics 2, there's some stuff in there that we'll certainly use, but not completely. It's mostly based on a DLD 1 kind of approach there. It's all digital logic. There's a little bit of analog stuff, so to speak, but again, it's nothing terribly concerning. And then as for DLD2, although it's mentioned here as a prerequisite, I honestly don't know what's going on in that class in terms of what's being covered. It seems like there's a lot of overlap between that class and this class from what I've seen, but I can't be 100% sure. Maybe you guys can give me some insight in that later when this class is done. But I think there was some material covered there in terms of sequencers and things like that. There's also, I believe there was some mention of a CPU device of some sort in there. Whatever. Okay. Well, as for our course schedule, we have 3 hours of lecture per week. Of course, that's what you'll see for most of your classes. Mondays and Wednesdays, 10 a.m. to 11:20. Again, these are live lectures. As always, attendance isn't mandatory, but I can tell you, I actually do have, data from you guys. Every time you enter these sessions, I do have that information. It is being recorded by the system. It tells me how long you've been in the, in the sessions, and I can look at that over time. And there's pretty much a clear correlation between student grades and people who attend the lectures. There's no surprise there. So, and I know sometimes students will say, oh, well, I just missed 1 or I just missed 2, and then it turns into 3 and then 4 and then 5 lectures, and before you know it, they don't know what's going on. So it's certainly good to kind of be on top of this. Also, you'll probably use a lot of this when you do your capstone project next year. Often a lot of people will use microcontrollers of sorts inside their projects, and if they have no real exposure to it, it's certainly more challenging. I will be doing participation marks though here. So while I do the lecture, I'll be popping up questions on the screen, and then you guys, of course, you answer them, and that will go towards your grade. As far as labs go, typically in person, I do have labs. You come in the room and you're given whatever lab has to be done, and you're given a week or 2 to complete it, whatever. So this is going to be a little bit different now. It's still labs, but it's pretty much going to be done through simulation, because I can't send you all the devices because we simply don't have enough of them, and they're very expensive. And what we're seeing is we're not sure if people are going to be sending these things back to us, which is a little bit of a concern. So we're kind of investigating that right now. So yeah. So during this time, I'll be on the system. The GA will be on the system. If you have questions, you can ask them. And I might, do a little session just kind of explaining what the lab is about, but I'll also do that in a little bit in the class as well when I assign them. All right. Okay, as far as the grade distribution goes, well, you'll notice here a word you don't see is exam. I won't be doing exams in this class because it's more of a fact-based class, not a computation-based class. So with that in mind, you guys could just easily, all do very well, and it's not really measuring anything other than your ability to, to use the find function, basically, in your PDF viewer or something like that. It's really nothing all that special. So everything is pretty much going to be assignments or laboratories or projects, whatever you want to call them. And that will be between 80 and 90%. So the actual grade distribution for each project, that's still kind of open, but I will say that no particular project itself will be worth more than 50, and that's obviously a Senate bylaw we have. So I certainly can't exceed that. So as for participation marks, we're going to be using a newer technology called iClicker, and this is one that you can use in a web browser or on your phone or on your tablet, whatever. And that will be between 10 and 20%. I'll kind of leave it up to you guys to kind of decide what number you want it to be. I believe last year it was 10%, but that means the other 10% went to your assignments. So again, I'll leave that up to you guys to decide. It's definitely got to be decided within 2 weeks, so I'll keep asking you every class. We did this last year because we weren't in person, so this way it works remotely very well. But we had an evaluation license back then, so it didn't cost anybody anything. Unfortunately, that's no longer the case, and the university hasn't made any decisions on purchasing a site-wide license. I think they're waiting on the government to kind of kick in something there, and I think the government's made some kind of announcements, but it's not really firm on that. So as it is right now, you guys have to pay for this. It's not a lot of money. It's only about, I think it's $15 to $16 plus tax. It's way better than the older technology we used to use. That was like over $60, but it was a device you actually purchased. But again, it could only be used in class. And I'll just remind you that we don't have any final exams. So I think this is pretty much. I wouldn't go to the iClicker site. It actually costs more money. So I will be posting a site for this. You can get it through the university bookstore. If you go to the iClicker site, it's something like $17 US. Here you'll get it for $16 Canadian if you buy it through the university bookstore. Okay, so I'll be posting something on the course website about the procedure to do this. I don't know the exact procedure because I would have to buy one myself, and I'd really prefer not to, waste money that way. Because as an instructor, I use the system for free in a sense, right? I can log in, I can create classes and all those kinds of things. So I don't see that one side of what you would see as a student. But I do have the student account. I've logged in there, and it basically, but again, my account's been a while, so it basically pops up a message saying, oh, you need to buy a license or something like that, or you can enter a code. So if you get it through the university bookstore, they should supply you with a code that you would then put on this website, and then you would have it for 6 months. And I know it's funny that it's 6 months as opposed to 4 months, of course, but that's what they do. There's also the option for a 12-month license, but it costs like $5 or $6 more, but I don't think anyone else is using this in their classes. Sadly, a lot of engineering profs don't use these types of devices. I'm not exactly sure why. But a lot of them are very old school, I guess would be the word I'd use. Okay. All right, so you guys think about that, and I'll pull up a poll, in the next class or so where we can kind of decide whether it'll be 10, 15, or 20%, something like that. All right, now as for the course content, this is pretty much taken from the course calendar. Can I use Kahoot instead? Kahoot is a very ad hoc kind of system, and it even has like limitations on class sizes and things like that. So if you have a lot of students, they want to charge you money. So we're not really far ahead. And believe me, I've been in discussion with the iClicker people about getting a site license or something that we could pay as the university. And there's just, I mean, for a company that's trying to sell something, they have far too many limitations, if you ask me. I asked them if we could just pay per class, and they said, oh, no, you can't do that. Well, can we set up a different organization just for that one class? Oh, no, we don't do that. I mean, it was just endless no's, we don't do that. And it's like, how do you expect to sell things to people if you don't accommodate for things? So they have a very rigid pricing structure, and let's just say I was kind of going back and forth with them for emails for over a month on a daily basis, trying to come up with some solution, and it was just it was clear they weren't interested in doing that. Pretty much just here, just give me your money and we'll give you what we want to give you, and that's it. So the only thing they were interested in was a massive site license where we'd have to pay them, you know, tens of thousands of dollars for every student on campus or something. And again, they're not going to do that for one class or a couple classes. Okay, back to the slide. So this class is basically on understanding how microprocessors work. Now, there's no surprise. There's certainly a lot of microprocessors in your life. There's all different ones you're using and you don't even know you're using. And even the ones you are using are extremely complicated. Your desktop PC is an extremely complicated microprocessor. But it's not something that you can learn from. It's not made for learning. And sadly, technology doesn't care about teaching people anything. They're only interested in selling things. So it's very difficult to find a device that teaches people how things work. That's not what they want to do. They just simply want to sell it, you know, maximize profit and move on, and, you know, phase it out and sell you something new in a couple months, right? That's pretty much how industry works. So we're going to be starting using very old devices, and the reason we're using old devices is so we can understand them. Again, new ones are optimized to no end to get the maximum performance, and those optimizations aren't obvious, right? You have to really have a good background to understand what they're doing and why they're doing it. Okay, so these earlier systems, and when I say 8 and 16-bit systems, we're talking about 1970s technology. So clearly the stuff we're using is much newer. I'm not sure what that means. Someone just wrote questions about 8 and 16-bit. So if you can clear that up, that's fine. Okay. Oh, well, sure. You can always ask questions here. Just ask the question. Don't ask me if you can ask a question. Oh, so it's the number of bits in which we, they're asking, what does it actually mean by 8 and 16-bit? What is the whole idea here? So every, just like cars, for example, you have different classes of cars. So you'll have, you know, your basic entry-level car, which is just designed to get you from point A to point B, and then you'll have, you know, like compact, for example, then you'll have mid-size and full size and luxury, and then, you know, sports, and, you know, just, you know, ridiculous after that. So we have the same thing with microprocessors, right? So usually when we talk about how many bits they are, it's the amount of information it can manipulate at one time. So an 8-bit CPU can only manipulate 8 bits of data in one operation, whereas a 16-bit CPU can manipulate 16 bits, and so on and so forth. So you guys are clearly used to hearing 64-bit processors. So your systems, your desktop computers can manipulate 64 bits in one single operation. So if I had to kind of compare, you know, an 8-bit system to a 64-bit system, that would kind of mean that my 8-bit system has to do at least 8 times as much work as the 64-bit system to achieve the same result. In fact, it's far worse than that. So, but, you know, maybe I don't need a 64-bit system to do something simple. You know, like my TV remote control doesn't have to be a 64-bit microprocessor inside. It could probably be an 8 or even less, or a 4-bit microprocessor to do, you know, the same amount of work, because it doesn't have to do a lot of work. So we never really overkill in electronics. We use whatever is necessary to get the job done. And the reason we do that is because it keeps costs low. So we're always looking to do this, right? How do I make money selling something? Well, I make money selling something by making it an attractive option for people to buy. But if my product costs 10 times more than everyone else's product, then don't expect me to actually sell very much. So this is why we have to kind of do this. We have to, you know, part of engineering is using resources optimally. So when you're building something, and if you're using electronics, you don't want to put in too much. You want to put in what's needed, what works, and that's it. If you put in too much, the cost gets too high, and no one will buy it. So we're still making 8-bit CPUs and 16-bit CPUs and even smaller CPUs because there's a lot of devices out there that's all they need. You don't need more than that. Certainly not desktop computers, but again, smaller devices. Okay. So data representations is how we interpret bits and what they mean, what they can mean. And I'll talk about the standardized ways we do that. Arithmetic units is just basically the systems that manipulate those data representations. I'll talk a little bit about the different memory structures. CPUs definitely use memories. That's the whole idea behind them. We're always using a different hierarchical memory system, again, based on cost, to kind of maximize performance and minimize cost. There's two different types of CPU designs. One is called a complex instruction set, and another one is called reduced instruction set. We'll be looking at both. Complex is easier to use from the user's perspective for programming, but it makes building the circuits much more difficult, whereas reduced instruction set makes building the circuits much simpler, but it's harder for us to kind of program. Okay, so going back to the complex instruction set, we talk about things like accumulator, index, and memory reference instructions, and something similar when we talk about RISC systems or reduced instruction set systems. So with complex instruction set systems, we have different addressing modes, so we'll discuss that. We'll discuss stacks. Stacks are extremely important to the way CPUs work. Without stacks, we can't have things like function calls and subroutines and those types of things. So that's pretty important concept to understand. And since we're going to be using a virtual microcontroller here, a microcontroller is basically a CPU with a whole bunch of other stuff connected to it. So it's actually like its own computer. So it's basically a single chip system. And so with that, we can do other things like interrupts and timing and interfacing with other devices or I/O devices. And hopefully we'll get onto how we can use. We'll definitely talk about using assemblers, but maybe if I have time, I don't know, how we can actually use C compilers and things like that with this. So all of this code implementation we're going to be doing, we're going to be using it's definitely an older microcontroller, known as the 68HC11, but it's certainly something we can understand. The devices after that started getting, again, far more complicated, and they're more about, again, selling than rather learning. So this is why I'm kind of sticking to this device. It's certainly old. It's not recommended for new designs, but we can understand it. That's the whole point. Okay, now as far as the textbook, there is a textbook for this class, but as you can see, it's not very recent at all, 2003. So there's actually, this is the 6th edition. There's actually a 5th and 4th edition, which are pretty much identical. I actually have all three, and actually I have even the ones before this, but the ones before this used a different microprocessor. So this series of books revolves around the 68HC11, whereas the other books kind of go back to the Intel, I believe the 8051 at the time. Now, you can't really get these books anymore. I mean, you can try to find them, but they're not available. So if just saying, you might want to maybe go look at the resource section at the Blackboard site right now. Just a recommendation. That's all I'm saying. In the next 5 minutes. There might be something there worth looking for. Funny how these rogue links appear. In any case, yeah, Blackboard is weird that way. Sometimes these links appear and just disappear at times. So just something. So if you can locate that textbook, it's, you know, good for you. Alrighty. And maybe if, you know, someone isn't here right now, you could help them find that, a place where you can locate that textbook. Okay, so as far as other things go, the website, so there's kind of like two websites, sadly. I mean, I can't really use Blackboard to do everything I need. This really could be an S here. I guess most things are like that now. So I don't have the course outline posted yet. I'm trying to kind of fit more in line with the standardized syllabus. So I'm going to be modifying my original syllabus to kind of fit more into that. So the course you see here, this is my own website, and here I have more control over the web server. I can do more things, but I'm obviously going to be using Blackboard for you to submit assignments, and also for just, you know, for security purposes if I'm not sure about the distribution rights of some material. Okay, so when you do go to the Blackboard site, there's a link at the top of the site. Let me just see. Well, actually, it's really hard. Again, I think you guys can go to this site. You can find the link to the 327 or whatever, 3,270 class, whatever it's called, and you'll see there's a link to the Blackboard site there that should bring you there. If you guys can just test it to let me know. And when you go to the Blackboard site at the top, there's a link to go back to this site, so you can kind of switch in between quite easily. So when I say, okay, the lecture material will be at this site, but again, any of the assignments will be on the Blackboard site. And if you have the Blackboard app, you can, you know, easily, you know, get notifications of these assignments. I used to use Twitter in the past to send out notifications just because, you know, it was easier for people without data plans to get notifications to their phone. But I think just about everyone has a data plan now. So I'm going to kind of stop using Twitter, and I'm just going to use the Blackboard announce feature to send out those things. Does everyone have? Well, let me just do a little poll here. I'm just curious if everyone has the Blackboard app on your phone. So if you guys can answer this. I just kind of, when I send out an announcement on Blackboard, I'm kind of bothered by the fact that it gives me the option to email it to everybody, which I think is, I don't know, just seems intrusive. So it seems like most people have it, and for those of you who don't, you probably should, because if anything, it just pops up something that says, oh, don't forget this assignment's due, or a new assignment has been posted, or, you know, whatever. And I believe you can even, correct me if I'm wrong, see these, you know, the live lectures through it as well. I don't know about the reliability. I don't know if I would use, you know, those features, especially if something important is going on. That's all. I recall last semester students were submitting, you know, their final exam through the app on their phone. It was like, I don't know if that's a good idea. You know, especially if the app crashes or something like that. So anyway, it seems like at least 66 of you use the app and 8 of you have fallen asleep, I'm guessing. So we'll put that away. All right. Now, I should probably change the time of my class. I mean, obviously we can't do this now, but some years are worse than others, let me tell you. So in the summer, for some reason, the government decided that every holiday has to be on a Monday, and our class and labs are on a Monday. So this kind of creates a little bit of a problem. So we have our 12-week classes, plus, we have the 1 week reading week in between. So basically 13 weeks of classes, but of those 13 weeks, at least the 12 that we're actively here, 3 of them are holidays. And this kind of creates a headache, certainly. So what the university does is, what the university used to do is just kind of make the semesters longer, and they would start on a Tuesday rather than a Monday or something like that to kind of offset this. And then, new people came in, new president, and they decided to, in terms of their ideas, make things better, but some might not agree. But so the end of the class, the last day of class, by their definition, is August 6th. But it's not really. So this is a Friday, right? Because we start on a Monday. We have these 3 days, these extra days, which are on the following Monday, the 9th, 10th, and 11th, which are all considered Mondays. So they're makeup days for our 3 holidays, Canada Day, the Civic Holiday, and Victoria Day. So these 3 days, the 9th, 10th, and 11th, are Mondays for you. So that means you're going to have, this class at 10 a.m., and then you're going to have labs from 1 to 4. Now, this does bring up a little bit of a problem with the one Senate bylaw that says we can't evaluate things in the last week of class. So on these 3 days, I can do in-class evaluation, but that's all I can do. So I will have some type of assignment that will be due only in class or in lab. So I'm just kind of warning you now about this. So you will only have 3 hours to get it done. And again, depending on how I work this out, I also have the 1.5 hours during the lecture time to also do something there. So again, in the last week of class, you can't have any assignments due. No, it's a holiday. These are holidays. The university is closed by definition. Sorry, the days listed here, not these days. The makeup days here are not. So these 3 days, we make up all of those Mondays. So the last day you can submit something is 1 week before August, well, the beginning of August 12th, which would be the end of August 5th, 11:59 p.m. So any labs will be due at that time. And sorry, just a fan in my other computer just decided to go nuts. It's just really loud. Right. So any assignment prior to that will be due August 5th by 11:59 p.m. And anything after that, and I'm going to warn you now, because unfortunately there seems to be this problem in our department in particular, where profs keep assigning things after this day. So if any prof tells you that there's an assignment due after August 5th, 11:59 p.m., you should tell him now, or her, that that's not allowed. Last year, or sorry, I should say last semester, every professor, with the exception of me, violated this Senate bylaw in every class taught. So we had to have a meeting and kind of explain to them, again, this is a rule, you can't do this. And, they'll always use some kind of excuse. Well, it helps the students. It gives them more time to get things done. It doesn't matter. It's not, you need to use that last week of class has to be, there can't be assignments due so you can study for exams. It's just that simple. So if they say, oh, you get an extension, it's breaking the Senate bylaw. If it's whatever, it's just unavoidable. Okay. Now, that being said, you can certainly submit things late, but if you do submit things late, I have a basic policy that says you get 10% deduction per day it's missed, and I do the deductions based on an hourly basis. So if you're half a day late, you only lose 5%. If you're a quarter of a day late, you lose 2.5%, for example. Monday is off for Canada Day. I believe it's still July 1st, is it not? Oh no, it's a Thursday. Oh, Yeah, I see it's on a Thursday. Okay, okay, well, just bear with me for a second. Let me just check the university calendar here. Reading week. Oh, okay. So that may be a mistake for me. Sorry. So that first day might actually be a Thursday, not for a Monday. Okay. So I may have to make those adjustments. Uh, yeah, I can see where the problem is. On the official calendar, it says makeup day for Monday, July 1st classes. It should be makeup day for Thursday, July 1st classes. This is actual mistake on the university important dates site. So, okay, so I guess that should be a Thursday. So, all right. Can the student who did that, who sent me that, I can see your name clearly here. Can you send me an email just to formalize this, and you'll get a bonus mark for that. So another thing I should note, if you find anything wrong with any of my published material here, I do give out bonus marks. So my published material, not, for example, the textbook or anything like that. So anything I post that I've written. All right. So I give up to 5%. So if someone submits, let's say someone submits 10 things that are wrong, and then someone else submits 5 things, then the first person will get 5%, the other person will get 2.5%. It's kind of graded linearly. Okay, so this should be, sorry, so the August 9th, and I'll contact the university about this, whoever maintains that information. This should be Thursday, July 1st. So this August 9th will actually be a Thursday for you. So any class you have on a Thursday, that will be happening there. I should also mention, this is something that happened in the past. A prof assumed makeup classes were just, an arbitrary day that he could just hold his own sessions, whatever he wanted. And let's just say that was a huge mess. Even though he was warned, he still did it. So in any case, if anyone says otherwise what these days are, just please, well, you can contact me first and I'll get the department head on it, or the associate dean, or just contact the associate dean directly. Again, I can't excuse other profs' behaviors, but I mean, I try to at least enlighten them. All right, so we're only actually going to have 2 days. Well, that's good. So I don't have to make up for so many things. Clearly someone did a copy and paste thing from last year. So, all right, that's better, because 3 days would be, well, I was just trying to figure out how I'm going to do that with 3 days, but all right. So I think that's about it. Are there any questions in general? Oh, don't worry, you're not, the lecture isn't over yet, if that's what you're thinking. I don't know if you guys can hear that grinding over here. It's one of my fans in the computer. I don't know what's going on. It just happened all of a sudden. I hate fans. But okay, all right. So I'll just do my little introduction here. Just again, you guys may remember this from last year. I kind of like going through it again, just to kind of explain the rationale for all this stuff, just so we can see old stuff. So someone asked, can we do the first 2 quizzes before deciding on weighing, on the weighting? I'm not sure what you mean by the first 2 quizzes. Does that mean just ask arbitrary questions, or? Okay, well, I don't, well, I mean, I suppose I could ask people about the weighting now, but I mean, there's 82 people in the class. Again, I don't know how many are conscious, but it's certainly, more than half. I believe there's 92 registered, so that's, I don't know, probably by Wednesday, this number is actually going to be lower. Who knows? I can certainly do that. And someone just asked about the makeups again. Okay, so let me just go back quickly to the makeups. And in the summer, there's, I should say there's 2 days, kind of forget this August 9th one here, but the 10th and 11th are makeup days for the 2 holidays we have on the Monday. Okay. So these 2 holidays, we need to make them up because the university is closed, so we picked the 10th and the 11th for them. So these 2 days will be Mondays on our calendar. And again, because the Senate bylaws, I can only have the assignments that I do on these days have to be due in class. So our normal assignments, I'll give you like a week or 2 weeks to get done, but these ones will have to be done in class. So you only have the 3 hours to do it. There's and because of that, I don't usually do any lates because that's basically I'm enabling you to break the Senate bylaw in that situation. I don't want to give people preference to say you only lose 10% if you submit it the next day. That would not be fair. So it has to be due in class. Okay. All right. So back here. Oh, sorry. Let's go back to this thing. So I can start doing this poll. Participation. Let's start out with some simple choices here. So if you guys want to give me an idea of how much of a weight you want. Now, do keep in mind, whatever you don't put on this goes to your assignments. It's always interesting watching a live. Oh, hold on. The quizzes, so the in-class quizzes, when I ask questions, are just basically based on the previous slides. It's just a way of me getting feedback from you. So I'll discuss the topic and then I'll ask them questions about it, right? So, when I sit here and say, after I present something and say, oh, do you understand that, right? So some of you, again, I don't have the feedback of being able to see your faces. Normally, if I look, across the class and look at the faces of everyone in the class, you can see the, I don't get that kind of face, or, and then you can kind of use that and kind of maybe go over material again. Here, I don't have that. I don't have any type of feedback. So the best I can do is just say, did you get it? And most people won't say anything if they don't. So this way, when you do the answer in the class, it'll tell me how many people got the answer right, or how many people picked A, B, or C, or something like that, right? Like a percentage. And based on that, and it's anonymous, right? So so that way, if you feel like, well, if I don't understand it, you don't want to say, well, I don't want to feel stupid for saying I don't understand it, right? So you don't have to worry about that supposed stigma, right? So, oh, and another thing I should say is that usually when I do this, and I've been doing this for years, I think it works out. You get 50% on answering the question, and then another 50% for answering it correctly. But I think last year, I think I made it a little bit more. I think I made it so you get basically 33% for answering the question and the other 66 for getting it correct. So, and the reason that was happening is I recall when we were doing it in class, there was, like someone sitting there that had like 5 of the clickers in front of them, and they were just pushing, buttons randomly whenever questions would come up because their friends weren't there. So they were kind of taking care of everyone. So I'd rather not do that. So I'll get back to you on whether it's 50 or 33%. I just have to remember how I have to configure the software to kind of do that for me. So someone asked, would they be numerical or just theoretical questions for the quizzes? Well, they could be both, right? If it's numerical, I'll present you with a bunch of options and you have to pick which answer is correct. So you might have to sit back and do the computation to figure it out. Okay, so far it's looking like most people prefer 20. Some people are there's kind of a race between 15 and 20, but so based on this, clearly 10 is going to lose. So how about if I were to eliminate 10, where would 10, or the people who've picked 10, where would you put your favor behind, either 15 or 20? I guess I shouldn't be surprised by that one. So it's looking like 15 is the favored amount here. Okay, well, I guess I could say 15 right now. I can ask again the next day to see if everyone still feels the same. All right, so I'll end it there. So it's looking like 15%. So that means the other 85 goes to these assignments. Okay, I'll stop the poll now. That seems a fair number. Okay. All right. So back to the in lab format. Oh yeah, so I'll definitely be using Logisim for this class. You'll be designing some stuff using Logisim. And again, I don't need to stress these things to you about Logisim. You know, it asks you for your student number. If you use parts from other people, I'll know. If you use a design from previous years, I'll know. If you try to subvert it in some way, I'll know. I can't stress this more than enough. I will know. So just don't do it. Okay? That's all I can say. Because every year, and I just did the DLD the DLD1 class last semester, there are still people who tried. I know. That's all I can tell you. Everything that's ever been submitted to me ever since I've worked here, I have records of. So any computer file, and guess what I do every time someone submits something to me? I check it against everything I've ever received. Okay, I have automated processes to do all this. It's effortless for me to do this, right? It's kind of happens automatically. So I can see when students submit a design from 10 years ago or something like that. I have all that information. So just don't. Okay, I can track it down to the exact person where it came from. All right, so again, just warning you, I know all the tricks because I've seen someone try them all. All right. Okay, so again, just to review, why do we do all this stuff? What is the whole point? Well, obviously, you know that we use semiconductor devices to build these digital systems. And one excellent example of digital systems are microprocessors. And this picture here is of a very old one, you know, the Pentium 4, only 45 million transistors here. And what's actually nice about this photograph is you can actually see the individual parts of the CPU. Most CPUs today, these areas here, I don't know if anyone can identify these areas, but they're easy to identify because they're very regular. And what's regular about them implies that, well, if the transistors are placed very regularly, this is more than likely a RAM device, an SRAM device in particular. Now, your CPUs today are pretty much dominated by these devices. That's where our cache is. The cache is a faster temporary storage of memory. And the CPUs today are completely dominated by that. So when you look at a CPU die today, you'll see like 80% of it is just cache because that's what makes it faster. Normal memory in your computer is very slow, so we have to do things to kind of improve it. Now, I'm not going to talk about that in this class. I have a fourth year class that discusses those issues, but that's predominantly what we're seeing. So the number of cores that really doesn't you could have 8 or 16 cores in your CPU. It's still going to take up very little real estate compared to the caches. The more cores you put in, definitely the more caching you need to put in. So regardless, just the fact that we can build these devices has made technology better in general, because now that we have faster CPUs, we can keep building even faster and better CPUs, and we use those CPUs to run simulations. And with simulations, we can do things that we couldn't do before. We can find out what's going to happen under different circumstances. We can do better analysis, right? Engineering prior to using CPUs for simulation was just it was a trial and error type of thing, right? You build something, did it work? No, okay, let's fix it. We'll build it again. Did it work? No, okay, let's fix it. We'll build it again, and you sell the thing that finally works. Well, if it's 3 or 4 iterations, who's going to pay for all that development? And it's always on the consumer, right? So how do we make things cheaper? Well, we stop the number of iterations of development. And this has worked out very well. The first IBM PC was over $5,000, and we're talking, early 80s money. Early 80s money, $5,000. That's a lot of money. You could be buying cars for that much money. Who would go out and sit there and say, well, I'll buy an 8-bit CPU for $5,000 with, half a megabyte of memory, or I will go out and buy a car. Like, a lot of people, that wasn't really a question. Right? Now, what are you getting? You can get a whole fully operational computer for less than $100. Really, you can. In fact, I don't know if you guys have seen those Android tablets that are $50. You get a screen, you got a lot of space. I mean, it's a functioning computer. And believe me, that just a low-end $50 Android tablet blows away anything we had in the mid-'80s. Right? So all of this technology allows us to build better and better things. We can, again, run more simulations, and we know how things are going to work out. So we build things the first time, and we get it right. So costs have certainly come down, right? So we're using these circuits to build everything, right? Microprocessors, we're using them to do a lot of things. Now, where has that gone further? Of course, all of our communications devices are based on these things, right? Before, they were very custom circuits. Now, they're essentially just CPUs, basically mini computers, essentially, right? So I like showing this slide because it shows 3 different technologies that are now all merged into one. Your cell phone, your GPS, and wireless router, this can all be inside your phone now. And it exists, it's all in there, right? So that we're seeing integration, we're seeing all these things coming together. And it's certainly not as big as all these things either, right? This is an original GPS, actually not completely original, but this thing was huge. It was pretty monstrous. Now they're pretty small, right? And again, wireless routers, again, in your phone, right? The technology to make these antennas, the software, everything is all integrated. Okay. As far as our high-end computer systems now, we still have these. We call them cloud computing. We used to call them terascale computing. We still have these very custom systems in very particular cases where they're dedicated, where they have all these processors and they do kind of work together. This was a system from at least 15 years ago. To think that it could have 74 terabytes of RAM, that's kind of outrageous back then, but we use those systems to do things that we couldn't simulate before, or things that we can't simulate. For example, any type of nuclear research is done through simulations, obviously, because doing this stuff with real stuff is not good. It's kind of frowned upon, right? I'm not saying people don't do it. People still do it. A lot of countries that shouldn't be doing it are doing it, and they're sanctioned because of it. But we kind of know. When you set off a nuclear blast, people tend to notice. I don't know if people ever realized, if you've ever watched quarry operations, where they're setting off explosions in the ground, and they're looking for whatever, iron ore or gold or whatever. They usually have timed explosions, so they don't just blow up everything all at once. They blow it up in a sequence of smaller explosions, and they have to do that because otherwise, it could be a false nuclear explosion being triggered, basically, is what it might assume to be done, right? I think a couple of years ago, North Korea did an underground nuclear explosion, and believe me, everyone noticed, right? Kind of shook the earth a little bit, right? That's what happens. So we don't do that anymore. We use computers. Also, for example, weather forecasting, those things like that. There's not just some computer on a desk in someone's government office that's doing, these weather simulations. It's massive computers that kind of do these very large simulations, trying to figure out what's happening, right? So, for example, in that case, they have like one smaller computer out of these massive systems that, that takes care of a, certain, I don't know, I'm just making up numbers here, but like 100 square miles of the Earth's surface, and the other ones kind of take another 100 square miles and another 100 square miles, and they kind of all work together to try to forecast what these weather events are going to be like based on that information. It's not something you can do with just one CPU. It just doesn't really work out. So, I mean, again, the term we use today is kind of cloud computing, but cloud computing is a little bit different. That's where you just kind of have access to some computer somewhere, but the real challenge isn't necessarily cloud computing. That's certainly driven the cost lower of these systems, but the real challenge is how do you get all of these independent processors to work together? So that's still an ongoing situation. Digital signal processing, that's changed the world a lot. Everything you're kind of witness to, even listening to this presentation, this is all encoded digitally, right? My voice is being recorded here. The picture is being captured from my computer screen here, but it's being taken and it's being encoded digitally, right? And it's being compressed and it's being broadcast, and then your computer's getting it, it's decompressing it, it's taking it all apart. And it's a pretty good representation. The occasional, you might hear some, audio noise, right? That can pop up from time to time, or you might see a video glitch, right? But it kind of corrects itself after a while, right? This is all technology that's been worked on for years past. Like just the technology you're seeing, the fact that you're watching some kind of like streaming MP4, that was developed decades ago, and you're kind of seeing it in use today. I think I asked this question before. Some of you might remember it. When was the MP3 standardized? I'm sure you guys have heard of MP3. It was the predecessor to MP4 audio. Does anyone remember this answer? Just chime in. '93? No, that's late. No, it's not in the 90s. It's before that. Definitely not the 60s. It was 1986. So the computational power in 1986 wasn't very good. So the people who developed it, I remember, reading the stories about this, and they were like, okay, we made a change to the algorithm, and then we ran it overnight to encode a 3-minute song. It took a whole night to encode a 3-minute song. If you can imagine that. And now what are we doing, right? So again, computers weren't very fast back then. So it took quite a while to work this out. And I remember when MP3s became popular when I was in university. And it wasn't until about 1994 that a desktop PC was fast enough to play one back in real time. You couldn't actually listen. You couldn't just play an MP3. You had to take the MP3 and convert it to an uncompressed audio file to actually play it on a computer prior to that, because it took longer than the actual time that the music was defined as, right? It would take 5 minutes to decode a 3-minute MP3 file. You couldn't play it in real time. Now, well, what are you doing, right? Just think about the optimizations in your computer to pull this stuff off. In fact, in your computer right now, when you play an MP4, on your computer. It's not a strictly software thing. There's a lot of hardware that's helping to accelerate that process because it's a very time consuming operation. So we have to do a lot of things to kind of make all that stuff work. But it just shows you that a lot of this technology has been developed for many years, and it takes time for it to kind of get to, just the consumers like us in terms of regards of, how patents are allowed to kind of be used in that way, right? If someone has a particular piece of technology, well, you can't just use it. You have to get permission to use it and those types of things, right? So lots of issues, and we'll keep seeing those types of issues as time goes on. So unfortunately, that's how, you can't just steal someone else's work, even though it's just because it's on your system. Just saying, it's the law in some cases anyway. All right, portable computing, this has certainly changed a lot. I don't know if any of you remember what this is over here. I remember seeing these things. This was amazing way back when, to see these computers that were so small that, look how big the CD drive was, right? Now this is not uncommon to see, right? In fact, your phone is very powerful, right? Your phone could be used as a desktop computer if it really had like a good way to actually input information into it. And there still really isn't, which is kind of sad that that you can't type on your phone faster and you can't really use it more efficiently. Oh well. But so yeah, this is an original iPod, not completely original, but this one had a color screen. The originals had black and white screens, but this is all been integrated right into your single phone. And and your phone is pretty expensive too now, right? So on top of that, that topic, device integration. So this was a phone from many years ago, and they took all these parts and were able to kind of put it all together onto smaller and smaller modules. And even now, this slide I think is 10 years old. So all of this has kind of been integrated into even more and more stuff. A good place to see what's inside your devices is to look at ifixit.com, which is it's a site that talks about how you can repair certain things, but they'll show you what's inside things. And you'd be surprised to see what's inside your phone. If you look inside your phone, you will see a very small circuit board, probably on the scale of something like this. And the rest is just screen and battery. In fact, it's mostly battery, because they can't make batteries better. And I know we keep hearing stories about, or news articles saying, oh, someone's come up with an advancement in batteries and so and whatever. But until it's commercially successful, like it's massive distribution, right? Bulk production, it's really nothing. Okay. Like for example, IBM made an announcement last week that they have a 2 nanometer fabrication process. Well, that's great. Well, they don't have a 2 nanometer fabrication process. They were able to make a 2 nanometer device, essentially. Now, what does that mean? Well, how long is it going to be before that's commercially available to companies to use so that they can sell it to you? That may not even happen. I remember when I was a kid and IBM wrote their name, IBM, the 3 letters, on basically using atoms. So the I was basically like 3 atoms across and maybe 5 atoms high and something like that, or 8 atoms high, whatever it was. Same thing with the B and the M. And they were saying, look at this technology, we can place atoms in this way. Well, that was over 40 years ago. It still hasn't come to market, because although they can do it in a lab under very controlled circumstances, it's not something they can do in bulk, right? So those are things we kind of always have to worry about. So right now, the battery technology is still, lithium polymer batteries, and that's what we're seeing, and that's what everyone's using, but they have their problems, right? So we can't pack more inside the battery, so we end up just making the batteries bigger. We make your phones bigger, thinking that, oh, look, this is better. Look at your phone, it's got a bigger screen. But what we're really doing is saying, this is how we're fooling you into saying, look, we're putting in a bigger battery. That's really what's happening. It's kind of sad, but that's what they have to do, right? They have to compete. If you're looking for a new phone on the market, what's the one thing they always talk about? It's the battery life. So how do you beat the competitor's battery life? You put in a bigger battery. That's really about the only thing you can do. As far as the software goes, what makes a phone slower is the fact that it runs so much software, and what makes it consume so much power is that it runs so much software. Can they reduce that? They can try, but that's a lot more work than just putting in a bigger battery. And people seem to want more and more features on their phone. So if anything, the talk time and the run time of your phone, or the standby time, is just going to get lower as time goes on. It just does. I mean, there's some enhancements, and if I get to the next slide here, as we lower our process technology, right, from 90 nanometer to 65, so you can see how lowering the transistor size. This is, again, it's just a symbolic graphic, but you know, so like 10 nanometer would be about here, right? If you can imagine where my mouse is kind of drawing, and now 7 nanometers about here. You can see how many chips I could put in 7 nanometer compared to 90 nanometer, and also the power consumption goes down. But you know, those are the positives. The disadvantages are it's a lot harder to build. It's very hard to get a working chip, so you have to invest a lot more money into well, what potentially might be something that doesn't work. It's possible. So this is the big challenge right now, is getting these technologies to build smaller and smaller transistors that are reliable and that we can use. Okay, when we build transistors, we can't just sit there and say, this is what I want, let's just build it. That's not really how it works. It's okay, we're able to get a functioning transistor. Okay, now how can we use this functioning transistor? We have to come up with a way to use it. So we're not really in charge of the building blocks that we generate or we build. All we can do is just try to take advantage of those building blocks. So as the transistors get smaller, their functionality becomes less and less and less. So we have to kind of find ways to work around it, and that causes more issues. Now this slide is particular about system on chip, and this is, again, just kind of going back to here, where you take all these parts and you can put them into one chip. So that's kind of where we're going, where, you know, since we can put so much stuff on a chip, let's put more and more into here. So we're starting to see more of that. I kind of would like to see even more, but you know, I guess it takes time to kind of get there. The more things you can kind of put onto a single wafer, you save more space. There's not as much wiring. And one of the things I'm waiting to see, they did this years ago, where they integrated the CPU and the graphics processor together, so you can make smaller computers. Okay, that's great. Okay, can we? The next thing I want to see is people integrating the CPU and graphics processor and RAM together. That way, it would be far better. But they are kind of like different technologies. The people who make RAM and the people who make CPUs use different processes. So there's got to be a lot of collaboration there to kind of move to that next step. Okay, so I think I'll end this here, at least this part here. Again, we're not done the class for today. So if there's any questions, just pop them up there. Otherwise, I will switch presentations here. I'll start with chapter 1. We still have 10 minutes. May as well use it. It all adds up after a while, you know. Here we go. Bear with me here as I switch over. I have to do this every time. Okay. So I'll probably just get through my introduction slides here. That's about it. Okay. Oh, I see someone sent me a private message. Okay, never mind. Never mind. That's not for you guys. It's from the GA. It's hard for me to see the private messages. They don't pop up immediately. Okay. So we've already been exposed to a number of digital systems before. We like digital systems because they're simply just easier to build, right? We have a lot of software that can help us build these things. So our digital systems, they have a very prominent role in our everyday life. So we call this now the digital age. All the technology around us is ubiquitous, and that's a term we use that implies that we don't even notice it anymore. there's so much digital stuff around you, you kind of see it all around you, right? In everything you use. We use these in communications, business transactions. The whole stock market is run off this stuff. Traffic control, spacecraft guidance, medical treatment. All of our imaging stuff in medicine is all built by electrical engineers. It's not built by doctors, believe me. Doctors didn't come up with an MRI or a CAT scan or all those types of things. Didn't happen. Okay. Weather monitoring, the internet itself, again, all done by electrical engineers. And then many other commercial, industrial, and other scientific enterprises, right? It's used everywhere. So primarily from your perspective, you have digital telephones, digital televisions, DVDs, digital versatile discs, or Blu-rays, whatever you want to call them, better storage, digital cameras, our handheld devices, and of course our digital computers, right? All this stuff is there. So we enjoy music and video downloading directly to our portable media devices, which are often our phones now. They have very high resolution displays and very complex digital networks. 4G, that's usually considered LTE or long-term evolution. You guys have probably heard of 5G. 5G isn't anything in particular. It's not like something special. It's just a very generic term, just meaning the next generation of wireless technology, whereas essentially all it is that we just have more bands and more frequencies to use. So like air, I don't know if you guys know this, air is not free. You can't just broadcast on any frequency you want. There's certain frequencies that are free to use. For example, Wi-Fi uses our 2.4 gigahertz and our 5, I believe 5, is it 5 gigahertz bands. There's also a 900 megahertz band. There's a 433 megahertz band. These are all bands that we can use, frequency ranges that we can use. Outside of those, they're dedicated to particular applications. So for you to actually use these things, you have to go to your government telecommunications representative, whoever that is, and in the U.S. it's the FCC, in the Canada it's the CRTC, and you have to apply to actually buy up some of this air that you can actually use it. Well, who wants all this air now? It's the cell phone companies, right? So they're trying to buy up all this air, and every time they get a little bit more of another frequency range, they can kind of add it to their pool of usable space. So 5G is kind of like the higher end, higher frequencies when we talk about that. So that's what's been happening lately, is where more of those frequency ranges have been brought out to be used for more I guess, for lack of a better word, residential use, right? People, just normal people, right? So the cell phone companies have to kind of buy up that space, and they have to have a way of using it, and that's where kind of 5G comes in, is just the next generation. It's not a particular technology, so to speak. It's just a term that means the next generation of. And it's sad to say that some companies will advertise their 4G as 5G, for example, right? But it's not necessarily wrong either. It's just these are promotional tactics, right? In any case, don't believe anything you read on the internet about what 5G actually is, because it's all wrong. Most people don't even know what it means. Okay, so as far as our phones go, these devices have very advanced graphical user interfaces. Okay, so someone asked the question, so it's illegal for a common person to use those professional walkie-talkies to choose what frequency they want. Well, anything that's sold that you can buy usually has some type of limitation in it. So you can't just broadcast with it. You might be able to listen, right? There's for example, you may have heard of like police scanners, right? This was a thing before where you could hear the police chatter. You can hear it, but you can't broadcast on it, right? So the device will let you hear it, but it won't let you broadcast on it. So if there's any type of walkie-talkie that allows you to pick some arbitrary frequency, those frequencies have to be within the range of what's allowable. If it lets you go outside of that range, then technically they're breaking the law. Now, I'm not saying you can't fix it to do so, but you're kind of technically breaking the law. Now, will anyone notice? Well, it all depends. many years ago in the 1980s, someone took over a television broadcast signal for like 5 minutes, and they still never figured out who did it because it just kind of happened. And whoever did it, obviously they stopped doing it. And how are you going to trace them after, right? You can't. So if someone is doing something long term, then yes, obviously the authorities can come in, they can trace it, they can find out where it is, right? But if you just do it for a couple minutes, well, it's kind of hard to kind of find out, right? So you might have heard of cell phone jammers, for example. A cell phone jammer will, it'll just broadcast out noise on the frequencies which cell phone uses, but can someone catch that person? Well, only if they bring in the right equipment and they can, triangulate it down and find it. But the person has to be using it pretty consistently to do that. Otherwise, it's very difficult to find, right? So this is for, people who would, it's again illegal to do it in general, but if you're doing it long term, then sure, someone's going to figure it out eventually. They'll find you, right? Just like anything else, right? If you go to the grocery store and you steal a can of beans once a week, are they going to find you? Probably not. But if you're stealing a can of bean, or can of beans every 5 minutes, eventually they'll figure out that, okay, who's doing this? They'll use whatever tactic they can use. It's just at some point it's just not worth it, right? So again, with anything else, but okay. Geez, it's almost 11:20. Okay, let me just finish up with this slide. So again, our devices, they're very advanced graphical user interfaces. Which enables them to execute commands that appear to the user to be simple, but which in fact involve very precise execution of a sequence of complex internal instructions. So what you think is easy on your phone, when you think it's easy that, oh yeah, there's just something here, I tap on this or I drag this there, there's a whole lot going in there. A whole lot of stuff is happening. Okay. And just as an example, your phone's operating system is over 4 gigabytes in size. That's 4 gigabytes of data and code. That's a whole lot of stuff going on. And this stuff has been evolving over the years. Okay. For example, Apple phones, the graphical user system used in an Apple phone is rooted back to the Next computers, which was a company Steve Jobs started after he got fired from Apple in the mid 90s. And that technology was taken from somewhere else. So, you're talking about decades of code evolving over time in time. It's not like someone just wrote this and it's like 10 lines of code to make this GUI system work. No, it's been a long time, right? So for you guys to use these things, I won't say it's easy, but it could be straightforward, right? You just, if anyone's tried to write an app for a phone or something, you basically just say, okay, well, create a box here or put a button here or do this here, do that there. That's easy enough, but there's a whole lot of stuff underneath that's that you're kind of ignorant to, and you want to be ignorant to it, right? You don't want to get involved in that. If you try to write that stuff from day one, you'll find out it's actually very difficult, right? So there's a lot of reusable code there. And it's nothing simple. Don't ever look at these devices and think they're simple, because they're clearly not. The amount of man hours, it's millions and millions of man hours to develop these things. It's not something that just happens easily. And every time they start building a new phone, they're not just saying, okay, let's start from scratch. No, your phone's OS, your current OS has parts of it from systems designed in the 1970s. It's code being reused and again evolving over time. It's like 50 years of software development in there. So there's certainly a lot of stuff. All right, so I guess I will end here. Oh, I forgot to mention, we would normally have a lab this week, right? And well, we aren't going to have a lab, but guess what we are going to have? Extra lecture time. Yes, I know, everyone is so happy. So at 1 o'clock today, guess where you're going to be coming back to? You're coming back here, back into this session, and I'm going to keep doing another lecture, at least another hour and a half. Again, I have to kind of make up for the time that I'm going to lose at the end of the semester because of those makeup days. I'm not necessarily losing it, but I'm going to use those makeup days for you to do assignments rather than lectures. So it all works out in the end. Okay, so please come back here at 1 o'clock. I'll send out a message, an